Let's consider delta, the difference operator. The delta operator between a and b of Sn is defined to be S evaluated at b minus S evaluated at a. Naturally, Sn is a sequence or function whose range has a well-defined subtraction. Let's cover 3 examples. The delta between a and b of n squared is by definition b squared minus a squared. The delta between n and n plus 1 of n squared is by definition n plus 1 squared minus n squared. We can expand n plus 1 squared into n squared plus 2n plus 1, and we can cancel out the n squareds to be left with 2n plus 1. The delta between x and x plus h of n squared is equal to x plus h squared minus x squared. Expanding x plus h squared, we are left with x squared plus 2xh plus h squared, and this leading order term x squared will cancel, leaving us with 2xh plus h squared. We assign 3 exercises to the viewer. First, compute the delta between x minus h and x plus h of n squared. Second, compute the delta between n and n plus 1 of the delta between n and n plus 1 of n squared. Third, compute the delta between n and n plus 1 of n to the m, where m is an integer. Exercise 1. Compute the delta between x minus h and x plus h of n squared. First, we recall that x plus h squared is equal to x plus h times x plus h, and distributing and simplifying, we achieve x squared plus 2xh plus h squared. If we change the plus to a minus, we get x squared minus 2xh plus h squared. The delta that we're trying to compute is by definition x plus h squared minus x minus h squared. Making the substitutions, we get x squared plus 2xh plus h squared minus the threefold quantity of x squared minus 2xh plus h squared. Canceling and adding the interior terms, we get 4xh. Exercise 2 is to compute the delta between n and n plus 1 of the delta between n and n plus 1 of n squared. To complete this problem, we must recall that n plus 1 squared is equal to n plus 1 times n plus 1, and we can distribute the n plus 1s to achieve n squared plus 2n plus 1. The delta between n and n plus 1 of n squared is by definition n plus 1 squared minus n squared. When we simplify this, we get 2n plus 1, and then we take the delta between n and n plus 1 of 2n plus 1. Substituting n and n plus 1 into 2n plus 1, we get 2n plus 1 plus 1 minus 2n plus 1. Simplifying and distributing, we get 2n plus 2 plus 1 minus 2n minus 1, which simplifies to 2. The second order delta decreases the degree of the polynomial by 2. Exercise 3 is to compute the delta between n and n plus 1 of n to the m, where m is an integer. To complete this problem, we must remember that we can take the mth power of a plus b by expanding with the binomial coefficients. A plus b to the m is equal to the sum from k equals 0 to m of m choose k times a to the k times b to the m minus k. In this case, a is equal to n and b is equal to 1. We also recall that the binomial coefficient m choose k is equal to m factorial divided by k factorial and also divided by m minus k factorial. When k equals m, this reduces to 1. By definition, the delta between n and n plus 1 of n to the m is equal to n plus 1 to the m minus n to the m. We can expand n plus 1 to the m as the sum from k equals 0 to m of m choose k times n to the k times 1 to the m minus k. 1 to the m minus k is equal to 1, and anything times 1 is equal to itself, so we no longer write this term. We also write the last term of the series as n choose m times n to the m. We also subtract n minus m, and these two terms cancel, leaving us with the sum from k equals 0 to m minus 1 of m choose k times n to the k. We leave the viewer with 4 homework problems. First, that the delta of a constant multiple of a function is equal to the constant multiple of the delta of the function. Second, the delta of a sum is the sum of the deltas. Third, the delta of a product fn times g of n is equal to f evaluated at the endpoint b times the delta of g plus the delta of f times g evaluated at the first endpoint. Fourth, the delta of 1 over fn is equal to minus the delta of fn over f evaluated at the first endpoint and also over f evaluated at the second endpoint.